because we're going to be doing everything in 3 dimensions this quarter, we need to be able to point in 3 space. So for example, when we talk about rates of change and the derivative, we need to be able to specify the direction we're going in, like a compass. So vectors are going to be the tool that we use to do that. Some of you might have experience with vectors from other courses like physics, but I would encourage you to at least go through the slides and the notes even if you don't watch the whole video all the way through. The main questions we're going to ask today are, for those of us for whom vectors are a new thing, what is a vector? What are the operations that we can do with vectors between vectors? What kinds of representations and notations do we have for vectors? And what are some of their properties? Okay? And then at the end, we'll do an example with some applications. So for the definition sounds a little vague at first. It's a mathematical object that has magnitude and direction. Now, vectors are inherently geometric objects. Okay? So their representation is just an arrow whose length corresponds to magnitude. Okay? So there's a vector, there's another vector, there's another vector, there's another vector. Okay? And I could move these vectors around. As long as the arrow points the same way and the vector has the same length, it's the same vector. For the notation, because I go back and forth a little bit here between using the fonts in Keynote and then importing some mathematical expressions, it's important to keep both of these in mind. So typed, I'll use bold V to mean a vector as opposed to V, the variable. And the way I would do it handwritten, which is how I would encourage you to do it, is to just put a little arrow over your letter to mean it's a vector. Okay, so in the slides I'll use both notations. In a book, you would see one or the other most likely. Okay, so just be comfortable with both of those. Now, how about operations? So all of the operations on vectors need to be definable just in terms of those arrows. Okay, so it's all visual, and then we get to how to do it algebraically. So here's how we add 2 vectors. We draw them tail to end, and then draw the resulting vector start to finish. Here's an example. Say I've got 2 vectors v and w, so there's w, there's v. Now we just said on the previous slide, we can move these around as much as we please. So let's draw v and w over here, and I'll draw them first tail to tail, and then I could draw v on the end of w, or I could draw w on the end of v. Notice that you end up in the same place either way, right? It's like if you walk 10 feet north and 5 feet west, it's the same as walking 5 feet west and 10 feet north. So the sum of v and w is the vector that connects the starting point to the ending point. Again, I have to reiterate, vectors don't have a fixed position. So every v that I've drawn here, and I know that they're the same because I just copied and pasted, those are all exactly the same vector. It's different from points, right? It's different from a lot of stuff that you draw on the xy plane, for example. Vectors can be moved around. The graph of y equals x squared is one location. You can't move it. Here's another operation. A scalar is a quantity that doesn't have direction. Okay, so every number you've ever dealt with up to this point is a scalar. You can multiply a vector by a scalar, and what it does is scales the length, that's why it's called a scalar, and it can change the direction if it's negative. Okay, so here's an example. There's the vector v, there's the vector 2v. So all I did is I made v twice as long. There's 1/4 v. That's a vector that's 1/4 as long as v. Now, if I multiply by a minus, then I get a vector in the opposite direction. If I multiply by a minus and a coefficient, then I get a scaled vector in the opposite direction. So all of these vectors are parallel. But some are longer, some are shorter, some point up and to the right, some point down and to the left. Now, as soon as I have addition defined and I have negative things defined, then I can talk about subtraction, because subtraction is really just addition of negative numbers. In other words, 5 minus 2, I should really think of it as 5 plus minus 2, and that's 3, right? Either way. Same goes for vectors. So v minus w, it's really v plus negative w. So the operation is still addition. So there's v, there's w, there's minus w. Now, I can draw these vectors wherever I want, so let's draw them to the right where we have some space. Here's the vector v. Now I want to add them, so I'll draw minus w tail to end. In other words, the beginning of minus w is at the end of v. And then the sum of the vectors gets me from start to end. Now, you could have gone the other way around, so you could have done minus w and then v, and you would end up in the same place. All right, so those three operations, addition, subtraction, scalar multiplication, those are all definable purely visually. But now we want to also see how this all plays out algebraically, okay? So say I take these 2 points, P1 and P2, and I draw a vector between them. I'm going to write that vector out in the following way. So a vector has a length and a direction. And so what it tells you is displacement. Okay? In other words, you could tell me that you're driving 30 miles an hour. You could tell me that you're driving north. If you tell me both of those things, if you say I'm driving 30 miles an hour and north, then I know exactly what your displacement looks like. So that's what this vector is doing, is it's telling you how do you go from P1 to P2? How far do you go in the X, in the Y, and in the Z? Notice that I've used these angle brackets instead of parentheses. That's because I have to distinguish between points and vectors. Okay, so please make sure that you use angle brackets when you're talking about vectors, parentheses when you're talking about points. Standard position is when a vector has its tail, its starting point at the origin. So the terminal point and the components that I have are, of the point that it points to, are the same. So the components match. In other words, take this point. So we could draw a line towards the y-axis and the x-axis. So there's the vector v connecting 0 to the point. If that point is the point 252, then the vector is 252. But again, you have to keep in mind that that vector can be drawn anywhere. So I could copy and paste it to the top of the slide, and it would still be the vector 252. It's just not in standard position anymore. All right, let's look at a little bit more of a concrete example. So if you're up for it, hit pause here and do the following things yourself. So draw your axes, draw these two vectors, put v in standard position, put w at the terminal point of v, and draw v plus w. Here's what you should have gotten. The vector 1, 2, if it starts at 0, 0, goes over 1 up 2. The vector 3, 1 goes 3 units to the right and 1 unit up. So if I plot it carefully, then it ends up at the point 4, 3. Because what have I done? I've gone 1 unit in the x and then another 3 units in the x. And I went 2 units in the y and then another 1 unit in the y. Well, the addition works out just like you want it to. You add the x's, add the y's, that's the new vector. Okay, so v plus w is 4, 3 in this case. Conveniently, pretty much all the vector operations work the way that we would like them to. So to add vectors, you add the components. To subtract vectors, you subtract the components. To multiply a vector by a scalar, you multiply all the components by a scalar. Here's an example. If you have 2, 3, 1 and 2, 3, 5, that's what v plus w gives you. Okay, so I just did 2 plus 2, minus 3 plus 3, 1 plus 5. Pretty straightforward. So again, orienting things in space is really important. Knowing when things are parallel is going to be really important. We saw that scalar multiplication always gives you something parallel. So if you start with 1, 2, minus 4, and you double it, or minus triple it, the two resulting vectors are both parallel to v. Okay, so 1, 2, minus 4 is parallel to 2, 4, negative 8, and I know that because the second vector is double the first vector. On the other hand, I can determine if two vectors are not parallel if they're not scalar multiples, right? Okay, so here's another example. Say we start with the two vectors. Can you find the scalar multiple? In this case, minus 4 works. Negative 4 times v gives me w. However, consider these two vectors. Why are these two vectors not parallel? Well, because if I multiply the x by 2 to get 2, and the y by 2 to get 6, the z multiplied by 2 doesn't give me 4. Okay, so 2 times 1 gives me 2, 2 times 3 gives me 6, but 2 times 1 does not give me 4. All right? Another operation. There's a lot of language that we use in this course that is synonymous and used in particular contexts. I don't really care about that a whole lot, so you can interchange synonyms however you please for the most part. The norm is just the magnitude, which is just the length. That's it. The only reason norm is a separate word is because if you have a vector of length 5, it has a norm, but it doesn't have a length because if it has 5 components, it's not 3D, so it's not drawable. 5-dimensional things are not drawable. So it doesn't make sense to talk about its length. But anyway, we're dealing with 3D stuff, so we don't have to worry about that. You can interchange the words however you want. This is the notation for the norm of a vector. Okay, it's like a double absolute value sign. Now, to make things easy, just imagine any vector you care about in standard position and apply the distance formula. For example, the vector minus 1, 3, 2 has a magnitude or length or norm, whatever word you want to use, of root 14. Okay, and I find that by squaring the components, adding them up, taking the square root, just the distance formula. Now, here's a question about the norm. What can you tell me about k times a vector? What's the length of that going to be? Well, I know that k is a scalar, hence it scales the magnitude. And I know that if k is negative, all it does is flip the direction. But that length is the same. So let's see if that intuition corresponds to the algebra. That's what the norm of kv looks like. right? A couple slides ago, we said that the way you compute scalar multiples is just multiply the k through. So if I put all that in my distance formula, and I square it all out, and I factor out the k squared, then I end up with this. It looks a little messy with the exponents and the subscripts, but that term in the square root is just the norm of v. So here's why this is a useful fact. It might seem really obvious to you, which is good, but it's useful because if I want to find the length of a vector that has really big components, I can just factor something out if possible. So if I had a vector 2070 minus 30, that's 10 times longer than 27 minus 3. So why not find the length of 27 minus 3 and multiply it by 10 instead of squaring those larger numbers? Yet another thing that's going to be really important down the road is the idea of a unit vector. So when a vector has a length of 1, it's called a unit vector. That's something that's going to be super important when we get to the concept of the directional derivative. You don't have to worry at all about calculus stuff just yet, but know that this is an important thing that's going to come back later on. So what we'll need to do in that context is take a vector whose length is something that's not 1, 5, 2, 3, a half, and make it of length 1. This is called normalizing a vector. So let's normalize a vector and see what happens. Say I want a vector in the direction of 2 minus 1, 1, but I only want it to have a length of 1. Well, scalar multiplication by a positive number, in other words, if I multiplied that by a half, then I would get a vector that's in the same direction as v, but half as long. Well, the length of that vector is definitely not 2, because it's at least 2, right? It's 2 units in the x direction. So I'm going to multiply it not by a half, but by 1 over its own length. In other words, I want to find the vector v divided by or times 1 over norm of v. So you take the vector and just divide it by its length. Okay, the length in this case is square root of 6. You could leave your answer like that. That would be totally fine. Or you could divide that through to each component and then get it in component form. There are 3 special unit vectors. These are the ones that point just in the x, just in the y, or just in the z directions. Okay? It should be obvious looking at these that they all have a length of 1 because all of them are telling us to just go 1 unit. Okay? Just go 1 in the x, 1 in the y, or 1 in the z. These get special names. So the x1 is called I, the y1 is called j, the z1 is called k. Alternatively, we can take any vector and express it in terms of i's, j's, and k's. And this is a common thing you see in physics, so I'm sure that a lot of you have already seen this. But for example, I could take the vector 2, 3, 6 and write it as 2i plus 3j plus 6k. Okay? For handwritten stuff, because again, you don't have the luxury of bold fonts unless you carry a ton of pens around with you, you could just write I, J, and K with hats, or if you write them with arrows, that's fine too. But oftentimes you'll see them with hats. All right, so that's all the preliminary stuff with vectors. I would encourage you at this point to pause, go back, make sure all the things we talked about so far make sense. And then in the next couple of slides, we're going to look at an application problem. So this is the very last problem in the practice problems. And it says you have a weight pulling with 100 newtons of force on these 2 wires, and the wires are at different angles. And the question is, how much tension is in each of those wires? Now the name of the game here is just vectorify everything. Okay, so I could represent the force that's downwards by a downwards vector with components 0, minus 200. Okay, I'm not going to draw it with a length of 200 because that would be kind of hard, so things here aren't exactly to scale, and that's fine. And then I've got a vector pulling in the right direction. Now, before I reveal the next thing, maybe pause and see if you could figure out what the components should be. If the tension on that wire is B, then the x component is B cosine of pi over 6, and the y component is B sine of pi over 6. Sorry, I know the pi's look a little funny in this font, but those are pi's. And then in the y direction, in the leftwards direction, I've got another vector. It has a length of a. I don't know what a is, that's what I want to find out. Except it's in the 3 pi over 4 direction, right? Because it's going to the left at 45 degrees. So it's actually 135 degrees. But just think of each of those as the hypotenuses of a right triangle, okay? And we want to write the x and the y components down. So once you have the picture vectorified, make sure that this makes sense. If it's unclear, you can come talk to me about it at some point or go to the Math Resource Center. Once we have everything vectorified, now we can get rid of the picture altogether, okay? If the weight isn't moving, that means the forces have to cancel out. That means the force vector on that point of intersection is 0, 0. So those 3 vectors, the one that goes to the left, the one that goes to the right, and the one that goes straight down, the sum of them has to be 0, 0. Well, we know what those cosine and sine values are, so let's put those in there. So the sum of those 3 vectors must be 0, 0. Or if you like, you don't have to do it this way, but the stuff you know, the constant terms, just stick that on the right-hand side. So add 0 minus 200 to the right, and you end up with that. Now, if 2 vectors are equal, the only way for them to be equal, not parallel, but equal, is to have exactly the same components. So I get a system of equations because I have the sum of the x's and the sum of the y's. And all that stuff has to add up to 0. Now from this point forward, you know how to do the problem, but it's messy with the square roots and all that kind of stuff. So in the next couple slides, we'll go through it together. Now, you can do elimination or substitution, or if you've done matrix stuff before, you can do it with matrices, but I like elimination. It works pretty easily here. So if I add the 2 equations together, I get that. Right away, that tells me what B is. All right, great. If I now substitute, so take 400 over root 3 plus 1, put it in there for B, and this is what the first equation turns into. So it's messy and cumbersome, but it's just some algebra 2 stuff. Like you're just plugging things in and simplifying as much as you can. So I subtract to the other side, and I multiply by negative root 2, and I end up with that. So that's it. Vector stuff is really important for everything we do for the rest of the course, so it's really important that all the stuff we just talked about in this lecture makes sense to you, that you're comfortable with all the notation, with the operations. So make sure to go through as many of the vector practice problems as you can. Come see me or go to the Math Resource Center to get help, and it'll go a long way moving forward in the class.